here, we're live, we're rolling, we're ready to go. Another great week. Hope you had a great weekend. Hope you enjoyed your Super Bowl. If you watched it, if you didn't, it was not at all what I expected. You know, I don't know that any of us expected a Super Bowl to look like that, but hey, here we are. So hope you're having a good time. Sorry for a couple of weeks of absence there from the streams. Had a lot going on. Had a surgery. Everything's looking good though. Um, Next week, if things still work out, I'm expecting to be in Florida for some YMC squareds. Doing some consulting there. But what I will probably do for next week is instead of being like a midday or morning stream like this, I'll probably do like an evening stream from the hotel I'll be at. I haven't quite figured out, and I want to be cautious because I don't want to step on Chris Stevenson's stream he does in the evening, which HVACR videos, right? He does his Monday evenings, so I don't want to have a conflict there. And I don't know how many of you actually watch his stuff compared to mine. We're in quite different sectors, but he has a really good stream. He answers a lot of good questions, so it's worth watching. Um, and I don't want to have a conf. So maybe I even do it like Tuesday evening or something. I don't know. Point is, I will likely be in Florida next week, and I do plan to do some kind of stream, which normally when I've traveled, I typically don't, but that's what I'm looking at this go around. We'll see. I did have an idea that I'm just going to kind of push out there. Before I try this idea, I want to catch up because I've got a pretty decent backlog of questions still. I'm hoping today we can really crush some of those. Um, but in terms of, I've thought about doing like a segment in the streams where I did like a model overview. So I'd pick a model and uh, we just do a full rundown of it. Of this is this chiller, this is what it does, this is some of its parameters, this is refrigerant circuit. I don't know. It's an idea. Think about it. If you have any comments towards it, just throw it into the comments. And it's something I'm playing with. But again, I am further behind than I want to be on catching up on questions. I want to get more of that caught up. I do see we have a question in the chat. We will get to that. I've got a couple of others I need to cover first, and then we'll get to the chat questions. So feel free, go ahead, start getting those into the chat. I'm not saying I'm behind on catching up on questions to deter you from posting your questions. It's why we're here. It's why we're live. I do prefer taking the live questions because we're actually here and we can interact if we need to. I'm just saying I have ideas, but I'm also trying to be cognizant of not bringing in new elements to the stream without really fulfilling our core purpose. Like we're here because of questions that need answered that you just having trouble getting answered somewhere else. That is the reason we're here. That is our goal for this time we spend. It's fun to hang out, don't get me wrong, but we have a purpose to be here as well. That being said, hi, let's get into it. So first question. I'm new in X19, so 19XR, so it's a carrier centrifugal chiller. Double stage series, so it's got a two-stage compressor. The 19XRs can come in single stage or two-stage, depending on the series you get. We can talk more about that in a minute. Just like to have an opinion to you if the chillers in 45% to 65% load had a condenser humming sound, lower load getting harder, higher load getting listened sound. All operation pressure is stable. Good chill water approach. Temperature and pressure stable. Good running operation. That's the only thing issues concern. Okay, so the primary concern is the humming sound at yeah, there's a humming sound somewhere between low load and I think you're saying it gets louder with higher load. So I've got two directions I want to go with this. Um, First, just hearing a humming sound. So humming noises in general, and we'll take this in the context of the 19XR. So if you're hearing a humming, I would I think of, okay, are we having a refrigerant charge issue? So with refrigerant charge, I would be concerned that uh, we're getting too low refrigerant. If it is actually coming from the condenser, and like low refrigerant charge would be a concern there, because as that charge gets lower into the heat exchanger, our velocity increases, and there's also the flask chamber inside of there with the float valve, and that float valve also has a bubbler tube, which is allowing a portion of discharge gas to come into the float assembly to make the valve work. Right. So with all of that happening, if we're running low liquid levels in the condenser for some reason, I would be concerned, uh, or I would expect you might hear some weird like swooshing, or you could call it humming, right? So the trouble with humming is there's how do we define that noise? Because here's the other thing, bearings. So if we're having a bearing issue, I've had a lot of technicians describe what I would honestly call more of a grumble as a hum. Or I've even had them describe, what you hear in a VFD as kind of a humming noise, right? Not exactly how I would think of it in my brain, but bearings can cause kind of, it's basically it's a harmonic resonance. You're hearing harmonics being discharged from somewhere in the system, and hearing it in the condenser, if can make sense, because that sound is traveling through the discharge line getting into the condenser from the compressor. And even though it may be actually, like, if you really really listened, you might actually be hearing a noise that's mostly in the compressor, but you can just hear it in the condenser because it's this big echo chamber off the discharge line. um, like, either of these could be potential problems. So if you're not hearing the bearings, which is more of a vibration problem, then we may be dealing with a refrigerant level issue. So as we lose refrigerant level, velocity increases, more noises get added. You can, a way to think of this is, you can sometimes hear with a like an RTU or a split system, when a circuit is starting to uh, run low on charge, or it's not making enough liquid refrigerant, you can hear the refrigerant running through the lines, and it has a different pitch and tone to it. And it's because there's not enough refrigerant, it's stacking into the system, and because the compressor is not slowing down, the refrigerant ends up gaining a lot more velocity as it cycles through the system in order to try to feed the compressor and make the circuit. So be, even though there's less refrigerant, you do increase the velocity, and that adds a lot of extra noise to the circuit. So that's where I think of, okay, are we having a similar condition here where that humming you're hearing, could it be the bubbler coming in? Maybe you're not maintaining enough liquid level, something to that degree. Now, a key point here is he did say it's a two-stage. So with a two-stage system, we have an economizer. It's a flash tank economizer, and it's located right there next to the condenser between the barrels as well. So again, it still has a float valve. It still has another, more of a flapper valve. That's really not a good description of it. I need to think of a good way to simplify what the economizer metering valve is, but it's still a float. Like it does have a float on it, but it's just different. It has a I'm just gonna call it a flap for now that opens and closes to allow less or more refrigerant through. Anyway, um, so there's, and this is assuming, okay, so I'm taking an approach here that all of your stuff is actually good, right? The approach, the water pressures, refrigerant pressures, temperatures, I'm taking the approach that you know what you're saying, you know what you're talking about. I would agree with your numbers and everything actually looks good, but these are our values. Or I mean, this is our condition, right? That's my approach to this. Outside of this, I'm trying to think what else we might run into that would cause a humming. To be frank, bearings is probably the one I lean into the most. Are we hearing a bearing problem? Is that causing some kind of uh, imbalance? The system's not running just quite right, or the balance on the rotors isn't running quite right because the bearings are starting to get worn and they're loose and they're just causing just an ever so bit of vibration, but it's coming through as like this humming sound because that extra vibration creates extra resonance, and that resonance is just being heard in the condenser. Like I really really lean into it's likely a bearing issue, but I'm not going to ignore that refrigerant charge can have similar conditions. Now we're going to pivot into another phase of this question that I think is a bit more important, and I want to spend a little more time on it. In general, in general, uh, if we are seeking somebody's input, and this is not a knock on who submitted the question at all, okay? Not a knock. This is just something as a manager, as a senior technician, passing down to people asking questions. Telling me pressures are good, approach is good, temperature, stuff like that is good. Like it's helpful. It tells me that we're not in an extreme condition, at least by your training, but it doesn't actually give me data to work with. And so what I would prefer in a scenario like that, if you're gonna like if you were to call me or something to try to ask for support and this is what you said to me, my very next question is, okay, sounds good. What are your actual numbers? What's the actual data here? And then with that actual data, it helps me get a much more clear picture because realistically, if we were having a refrigerant charge issue, like I'd mentioned, see that in the numbers, but they may be subtle. So while they may be technically within range, here's an example of what I mean. So let's take approach, for example. On that machine, I would expect our approach to be less than 3 degrees Fahrenheit. Okay? So less than 3 for evaporator approach specifically. All right. But that is at a full load. So that's with a 10-degree temperature difference. So if we were running a 3-degree flat, if we had a roughly 10 degrees, 8 to 12 is, but most machines are designed for about 10 degrees Fahrenheit. Make that an F, not a T. So, or I don't know what I was doing there, TD. 10 degrees TD Fahrenheit. So, if for some reason, let's say the machine was only running a 5-degree TD, and we had a 50% RLA on the motor, but we were still running 3 degrees approach. That's going to throw red flags right there. It's subtle. If you haven't seen that, you may not know any better. Okay? And it's easy for you to come with the approach, or it's easy for you to come to the conversation with, hey, my approach was good, all these numbers were good, I had a low load, but all my numbers look good. It's like, well, okay, 3 degrees at 5 degrees temperature difference when we're designed for 10 and we're running the compressor's only running a 50% load. That's no, I would rather this be like half a degree, 1 degree. Like you've got very little load. We should have no reason to need a 3 degree approach at that low of a load. Why is our evaporator approach there? And this could be an example of what low refrigerant charge could look like. It's low enough to be an issue and to start causing symptoms, but not low enough to like shut the machine down or go into low pressure faults or things of that nature. We're not maintaining enough liquid refrigerant in the system in general. And again, that gets back to that original point. You may not know that. And that's okay. That's why you're asking questions. That's why you're learning. That's why we're having this conversation in the first place. So this is why I ask for numbers. This is why, like, when we're gonna have an in-depth conversation and you need that support, I need more data. It's not that I can't do anything with a basic explanation of like what this question is. Again, I'm not knocking the question or the person who asked it. I'm just trying to give some context to you so that you can, maybe I can explain this in a way to help you understand why we need the data so much. Because this is a very real scenario that you could have. And if you're just going off of these are my min and maxes, like ballpark ranges, you'll completely miss it. Completely miss the diagnostic, and you'll be where you're trying to figure out what's going on here, and you're not gonna know that this number is dependent upon full load conditions. You're at partial load conditions, but you still have this number. No, all these numbers should track together. Partial load, much lower approach. Anyway. So, in a scenario like that, what is some really core relevant data we really, really, really want to have? Okay. We're just talking some bare minimums here. So, yeah, basic data. I want to know my approaches. So, evap / condenser approach. I also want to know my saturations. Okay. My motor current. Now, specifically, percent RLA or FLA, whatever you're looking at. So my motor current in percentage of that motor. You can give me the actual amps, right? But the percentage, it means far more, personally. So I want to know what is my RLA percentage, and then approach, saturations, and this is both on condenser and evaporator, and this from a context of a water-cooled machine. This still matters even with an air-cooled, because the approach I'm looking at is, okay, what is my TD between condenser saturation and ambient on an air-cooled? That still matters, and that's going to depend on the machine, whether we're looking at 20 degrees, 30 degrees, 25, whatever, it still matters. So air-cooled, water-cooled, these numbers aren't really changing for me. It's helpful if I know metering valve, or if I have that data, so metering valve position, I'm going to say MD position. Really helpful. That's not going to help you with a 19XR, okay? There's no electronic control of the metering valve there. It's fully mechanical, so that's not going to do you any good. It's just if you had it available. What else would we're just talking bare basic numbers here. If you have it available, discharge superheat. If I could write today. Not really, I guess. Discharge SH. Be really, really helpful. again, that's going to be more specific to larger tonnage machines like centrifugals and such. If we were talking air cooled, you would also want to have your suction superheat as well. But at a bare minimum, what's my discharge superheat in the context of this 19XR? Um, with these, we can do a lot. Now, some extras that'd be really helpful would be like our heat exchanger DPs. So knowing our differential pressures. Now, again, if I don't know what the design differential is, that doesn't really help me much. But I can kind of get a feel for just, is this maybe extreme, or do I typically see? So okay, on a 19XR, let's say this was, did we get a tonnage on that? We did not. Let's just say this was like a 500-ton machine. Would fully expect around, what, 3 to 6 psid for most of those, if memory serves. And if we saw 1, or if we saw 12 psid, gonna have questions. Okay. But if we were close to that, like I said, that 3 to 6 range, smaller machine, probably going to be fine. Not too worried about that. And that's just, again, we're just talking high level numbers here, just to get a basic direction, because that's a lot of what we're trying to do when we approach a situation like this. We need to get a basic direction. We need to eliminate what we can and start working through a list of possibilities. Nope, I don't think it's that one. Nope, I don't think it's that one. So, for example, are we dealing with a high pressure scenario? Is it having low pressure issues? Are we having an oil pressure issue? These are all possibilities that, based off of this data, we can start scratching off the list. Now, based off of the question, the assessment that none of those issues are the problem, and we're kind of to a point of, well, I don't know what the problem is because all my data says these other things aren't a problem. That's just, we have to just continue working through the list of what the possibilities are. But that also means getting enough training and background and understanding to know what to do with the information. Okay. Yeah. If you can, try to have that data. It makes a huge difference. And I don't, especially if it's somebody, even if it's somebody you work with, they may not know what you were taught good approach is. And your definitions of a good approach might be different for valid reasons. It's not that one of you are right or wrong necessarily, but what I call good approach and what you call good approach might not be the same. So let's be careful to assume they're the same versus just using the data itself to show our opinion. The data itself is far more useful when we start working together to collaborate to figure out what is happening, what do we want to have happen, and what do we not want to have happen. Okay. Yeah. Good question, though. All right. Let me catch up on some of this chat here. A2L. Yeah, from a controls transformer. Actually, that is a fair point. The controls transformer. Granted, I don't know, because the on those 19XRs, the drive panel is mounted on the condenser side, so I mean, I don't think you would have a, I don't know. I'd advise anyone who's stuck, fill out a log sheet. Yes. Yeah, fill out a log sheet. Yep, I absolutely love that recommendation. Good point, Jason. And that is actually something I did early on. I can do it in my head now because I've just done it so much. But early on, I actually had a laminated um, sheet that had like a basic refrigeration cycle drawn on it. And I carried an expo marker with me. And if I walked up to a call and I was having to work through it and I just didn't, it wasn't obvious to me, that is legitimately what I did. I just expoed all my numbers. I didn't try to process anything. I just went through, wrote everything down on the paper, took a step back, and I just looked at the data. And I mean, I did this for a few years in the beginning until I just got my head around troubleshooting and just continued improving from there. But it is, for me and for some of us, it is incredible just how much it can filter out the noise in our mind and just really help us hone in on the specific information that we need to understand our scenario in front of us. All right. I tell you what, let me see. Let me check. Good there. Oh, I want to get into a couple of these. Let's dive into some of the comments, questions, and then we'll see about the others later. Next one up. Okay. What are your feelings with A2L chillers coming out? It just different refrigerant, really. Um, yeah, they're just different. I'm not really too like I'm not worried about it. It doesn't scare me. There's dangerous things to everything that we do. We have to be careful either way. It seems like venting, not that you really should be, but like purging your stuff out might become a little more important than what we've done in the past. Let's see. It's caused a lot of interesting issues that I don't think any of us saw coming. For example, it's caused Train a lot of bearing failures with their, because I think, now that I say that, is 514 an A2L? We can look that up. I'm actually curious. Is 514 considered an A2L? One second. 514 and A2L. Probably should know this on some degree. Let's see. For non-flammable. Okay, so 514 is not a. It says it's a non-flammable, which I would assume means non-A2L. Okay. The new refrigerants have caused some interesting things. The point I was gonna make with 514 was the bearing issues it's caused, but as I verify, it's not an A2L, so we can bypass that. But yeah, thank you, Jason. HFO. Either way, it seems like it's gonna work fine. We're gonna adjust. We're gonna get used to it. There's always change and just constant evolution. I do think a lot of this stuff is forced for market reasons. Like it's wrapped up in these pretty bows as to all these, we're for the world kind of agendas, and it's fine. Like marketing is marketing, but a lot of this stuff is just more stuff gets sold, more new stuff has to be sold, more regulations means more markets market capital being used. Regardless, I'm fine with the A2Ls. Like it doesn't bother me. Not worried about it. It's another refrigerant. You know, when we made the transition from 12 and 11 to 123 and 22, all kinds of issues came up then. When we made the transition from 22 to 410A, quite literally, the shop that I started, like my very first job in the industry, working as an apprentice, they would not allow us to work on 410A systems. Why? Because it was too high pressure. It was dangerous. It was dangerous to work on because the pressures were just so high. It was going to burst pipe and rupture and cause all these issues. Like, that was literally the conversations we were having at the time. I'm not even joking. Like, that was a real conversation. When we walked up to a unit and it was 410A, we were told to walk away. Don't touch it. Only certain people in the team were allowed to mess with it because they were the only ones that could be trusted with a high pressure system like that compared to R22. Now, if that sounds absolutely ridiculous in today's world, that's where my mind goes. When I hear and I see a lot of the concerns about A2L, it doesn't mean they're illegitimate. It doesn't mean 410A being a higher pressure shouldn't be something you consider or think about. But I think we'll have a very similar conversation 10, 20 years from now, whereas just it ended up just not really being that big a deal. Yeah. I mean, so that's where my mind goes. I've seen it before, been there, done that. I've been through these processes multiple times now. It's just another one. It's a different change. It's a different switch. Um, we just got to retool, readapt. Maybe we add a few extra procedures that were more loose. Many of those, to be frank, most of the procedures that I've heard should be followed with A2Ls are technically things that by the book were things we should have been doing anyway. By the book. Is that what we typically do? No, most of the time we're not. But should have. And now it's going to be something where it's more risk if we don't. So if we're going to continue not using those practices, like purging our equipment out and making sure that all of the gases are out and we don't have any like minor eruptions. And I say minor, sometimes they may not be so minor depending on what you're working on. Um, yeah. Hopefully that's a sufficient answer. I'm not trying to just give a blah BS answer, but I'm just trying to answer honestly, like where my mind is at with it, how I think about it, how I feel about it. Like that's my goal there. Okay. Let's see. Next up, how you doing from India? Let's see, what's your condenser approach? Yeah, let's talk about it. Okay. What's your condenser approach? This gets back into just some very fundamentals that we heavily use in chillers, and we use it less. When we do use it elsewhere, we think of it in different context. So, a simple way to think of approach is okay, if you're looking at your condenser saturation to outside ambient air and that temperature difference, that TD between there, or the delta T, whatever anybody wants to call it, um, it's technically TD. Delta T is the difference between like entering and leaving. Your TD, temperature difference, would be your saturation to ambient. So if you do that on an RTU or split system to see how's your condenser running, well, you've basically taken an approach just in an air-cooled format, and we don't commonly use the term approach in the industry. Like, that's not the standard word we would use with that equipment. In short, we use approach with more water-cooled equipment, and when we start getting into chillers, which the definition there would be a machine that has a hydronic evaporator, meaning we're cooling a fluid in the evaporator, but we may have an air-cooled condenser. Well, even that evaporator has an approach as well. So it's really, whether you're talking evaporator or condenser, it means the same thing. So it is, let's see, we'll start with condenser. So a condenser approach is the condenser saturation minus condenser leaving water. So I'm going to say LWT, leaving water temperature equals your approach. That'd be your condenser approach. On the evaporator, it's the other way around, where we have evap leaving water temp minus evap sat equals evaporator approach. That's the formulas for how you're going to get either number. We're just looking at leaving water, subtracting our saturation from that. The leftover value is the approach value. Now, this will change based off of the type of heat exchanger, but let's hone in on the condenser side. So the condenser approach is usually going to be on just a shell and tube heat exchanger most of the time. So these are on a water-cooled, so a water-cooled condenser. We're talking shell and tube, typically. There are other versions. We're going to have a 0.5 to 3 degree Fahrenheit approach. Now, most of these machines are designed that at full load, we would have 3 degrees. And then as load is reduced or as the heat exchanger becomes more efficient, we are going to see that number drop. So even at full load, you may have a 1.5 degree Fahrenheit approach. That's great. You're doing good. It's just that it's not abnormal to see up to 3 degrees at a full load. Now, it doesn't mean that there aren't special cases where the manufacturer designed for something specific or unique. I have manufacturer trainers hit me routinely because they're like, oh, well, it depends on the machine, And there are machines that are designed with unique characteristics that are specific to them. Fair enough. Vast majority of machines, that is not going to be true. The vast majority of what you're going to run into in the industry is going to fall into some basic parameters that we can use to get where we need to go, to understand what we're seeing. Okay, so back to the core question of what is your condenser approach? So it is the efficiency of the heat exchanger, of heat exchange. So, of heat exchange. Meaning that the better our heat exchange is, the lower the number is going to be. This is why the heat exchanger itself matters. When we get into other types of heat exchangers, they run higher approach values because they don't exchange heat as well as the shell and tube. So an example I would give here is, let's say you were working on a little water source, water-cooled unit, and it's got a tube-and-tube condenser on it. Those condensers typically run more like 10 degrees of approach versus 3. It's just because it's less efficient. It does not do as good of a job. So the because it doesn't exchange heat as well, we have to create a larger separation, a larger temperature difference to transfer heat at the same rate or at a high enough volume. There we go. To transfer the heat at a high enough volume, we have to increase the temperature difference because it is less efficient at moving the heat from the refrigerant to the water in the tubes. So because it is less efficient, we need more difference to move the heat at a high enough amount. The more efficient the heat exchanger is, the less of a difference we need between saturation and water temperature. So the less of that difference is required to transfer the BTUs we need. So, and we'll take a evaporator approach to this, okay? No pun intended. So let's you look at a braze plate heat exchanger. So a braze plate, and this is where we can stay within the context of chillers here. So a braze plate, it's common at full, we're going to stay with a full load scenario. So that full load is common to have 8 to 10 degrees of approach. Okay? And with a shell and tube, normally at full load, we're going to be about 3. Some of them could be 4, but about 3 degrees at full load. Let's say both of these were put on a 200-ton machine. So we had a flooded shell and tube. Guess I should have identified that. So a flooded shell and tube heat exchanger and a braze plate. And both of them were on a 200-ton machine. Okay. So at full load, we're transferring 200 tons an hour of heat through each of these evaporators. To do that, we have to get a much bigger difference in temperature between the water temperature and the saturation of the refrigerant to move the same amount of heat that the flooded shell and tube can do with a lower value, a lower difference. That is a side-by-side of like how the efficiency is being affected. And again, this conversation is the same whether we're talking evaporator or we're talking condenser. It's the exact same principles. It's just one is the high pressure side of the system, one is the low pressure side of the system. But what is happening in the heat exchanger is the same. Like this heat exchange process with approach. Things that can affect this. Okay. Fouled tubes. So if we're having a high approach issue, tubes may be dirty. We could be having a refrigerant charge issue. Could be high or low charge, depending on the scenario. Oil logging. Now, both of these would be both evap or condenser. Oil logging is typically going to be an evaporator issue. Most of the time, you're not going to see oil log problems in the condenser, and it's just based off of design, and that's a whole nother rabbit trail we could dive into. But if we start stacking, what I mean by logging, we start stacking oil in the heat exchanger, which would inevitably be the evaporator in this case, that's going to cause approach issues. It wouldn't be any different than having fouled tubes. Fouled tubes and oil log will have very, very similar symptoms. Very similar. It comes back to just how well are we moving the heat. The harder it is to move the heat, the more these numbers increase. It gets back to the same principle. We have 200 tons of cooling to move. And the better we can do that, the lower these numbers have to be. But the harder it is to do that, the higher these numbers get, the more our compressor amperage increases, the more work the machine ends up having to do for the same 200 tons. Like a lot of stuff pivots off of these values. It's why they're so important. It's why we emphasize them so heavily. Another way to say that is your COP is significantly affected based off of this. Something to research if you don't know what that is. All right, fouled tubes, refrigerant charge, oil logging. GPM is also on the list. If we're having a flow issue or a GPM issue, even if the tubes are clean, that can cause approach issues. Or it could just be, temp sensors. Or just sensors in general. Whether it be pressure sensors, temperature sensors, we could just have some kind of sensor issue going on that we're not reading the refrigerant correctly or we're not reading something correctly. And that is leading to false readings. Okay? So just kind of many times, like always verify your sensors. As I'm thinking through this, always verify your sensors. Make sure your sensors are reading within calibration, which what that would mean. On a transducer, typically we want to be at an absolute maximum, no more than 5 psig off from calibration using a calibrated gauge. And even then, depending on the machine, that you might be more like 2 or 3 psig. If you're more than 2 or 3, no more than 5, that transducer is out of calibration if you're outside of those ranges. And then we usually use a firm 2 degree 2 degrees on temperature sensors. So if the thermistor is more than 2 degrees out, plus or minus, is done. Change it out. So if you're seeing that, then include your water temp sensors, your refrigerant temp sensors, your pressure transducers. Those need to be verified when we start questioning approach and stuff. These are much easier to deal with than the rest of this. So if you're having the rest of these issues, or don't think you're bad sensors, can also make it look like all of this. Just bear that in mind. We have to, one of the core basics, we have to make sure that our sensors are accurate. Even if somebody's recently done a maintenance, that's not sufficient. Verify yourself on site. Don't let this make you have a mistake you could have avoided. Condenser approach, high level, that's what we're looking at. Now if you would, give me just a second. We had another grass fire come in. That's fun. I had one yesterday up here just north of my house. Yeah, I can't make that one today. We're busy. I'll see how they're doing after the stream here. We got to do this. Okay. Yeah, we haven't gotten full reports on yesterday's fire yet, but it was pretty gnarly. Thankfully, we ended up doing a bunch of back burning and got everything under control and burned off all the additional fuel. That's where it got in. It's so deep into the brush, and there's so many valleys and ravines and stuff we get into in this territory we're in, that lots of times it is easier to get out ahead of the fire and then find some nice open spots, start a back burn it back, and then at that point that become a really good fire barrier. And at that point, just protect the barrier. Once you get the back burn started, so you're intentionally burning part of the land leading up to where the fire is headed, what we call the head of the fire. You're intentionally burning that land, and we're burning back towards the fire so that we create this large barrier zone where the fire then has nothing else to burn. And if we can then just patrol that zone and protect it. And that's what a lot of yesterday was. Where the bulk of the fire was so hard to get into. It's easier to do the back burn and then just protect. But yeah. Oh, we just got canceled. Okay. See, that's good news. When we get canceled, it's good news. It means they got it. There's an AHU installed under one of our ceilings in our lab. One day the maintenance team came and did something. There was an unusual sound coming from our plaster of Paris wall. Itself is vibrating. So it may be hammering. So yeah, on that weird sound after they did some work on the unit in the ceiling, it may be just water hammer, depending on what they did. Or if it's not water hammer, then it may be velocity. If they changed the rate of flow or something, maybe they increased flow through it. That so you could be hearing water velocity flowing through the pipe. It may be hammering occasionally as the valve opens or closes, or like those would be the two thoughts I would obviously jump to hearing that. So yeah, let's see. Could be normal as well. They're loud machines. Just catching up on chat here. Refrigerant level control valve continues open. Let's see. All right, so refrigerant level control valve. I mean, what you were talking metering device of some kind. Now, I don't have any context as to what machine or model or make you have, so we could be talking about an EXV, we could be talking about a variable orifice. So that would be an important piece of information. Uh, I say that, yes and no. Continues open. So in the context of, let's say, a York YK, if those valves, if we go into shutdown, those valves go into full open at shutdown, which is different than most EXVs. So if we're talking about a system with an EXV and has a liquid level controlling the metering device, then those will close off at shutdown and isolate the condenser, and it separates the two sides of the system. So depending on the style of metering device, depending on the machine you're working on, they have two different modes of operation. So your YKs, YMC squareds, YZs, those Yorks with variable orifice valves, those go to full open at shutdown. But like an RTHD, RTWD, your air-cooled screws with EXVs, like all of those are going to shut the valve at shutdown. Dun & Bush uses a liquid level control on their evaporators, right? Those valves, again, they shut down at shutdown. The metering device closes. So in terms of during operation, valve continues to open. It could be it's likely going to be a sensor problem. Whether your refrigerant level sensor is not calibrated correctly, not reading correctly, and let's just say maybe I'm reading into it too much, and you don't have liquid level control, even though that is my assumption here. Maybe you've got maybe you're basing it off of discharge or suction superheat. Well, again, it comes back to whatever those readings are. if we're not making set point. So if we're using superheat, then we're going to have a superheat set point that we're trying to target, and that valve is going to control based off of that set point. So if we're not meeting set point, the valve's going to open, which may be incorrect. It gets back to a bad sensor. Do we have a bad sensor somewhere and it's causing us to overfeed or underfeed, or I guess open, so we overfeed the evaporator, which could, like, that's part of what we've got to diagnose there. Are all of our temperature sensors acting correctly? Is our refrigerant level sensor calibrated correctly? That's what I would want to be diving into. Where are those sensors? How are they functioning? When we start getting into level control issues, that's what a lot of it comes down to. What is the sensor telling the valve? Now, there are going to be some scenarios where if we have a low charge, that may be partially why. So if we have a low charge issue, it gets back to what is set point, then we may see the valves go to 100% position. They're feeding as much refrigerant into the evaporator as it can, strictly because we don't have enough refrigerant in the system. All it can do is just open to full to try to satisfy whatever set point. Now, in the case of a YK, or a York water cooled with a liquid level sensor in the condenser, if that sensor is reading high continuously, then it's going to force the valve to go into full open. Most other machines are monitoring level on the evaporator. So on a machine that monitors evaporator level, if the evaporator runs low on refrigerant level, it's going to open the valve and it's going to try to run full tilt. That's just one difference you'll see between these York water cooled and other brands. They're just controlling based off of different values, but the control logic flips either way. So high condenser levels, valve opens; low condenser levels, valve closes, things like that. But it's also where knowing that our refrigerant charge is really spot on. So you're going to see that on like these, just about any screw air cooled. They're monitoring for discharge superheat or suction superheat, either or, depends on the machine. And if we're not hitting that set point, we're running high temperatures, discharge and suction, we're going to open that valve up. But if there's not enough refrigerant to constantly feed, maybe it's enough to make the machine run, but we're seeing the valve run at 100% position, which is not a good thing. They should be able to run at a midpoint for their control. Well, that's where we want to see what does our charge look like in addition to where is our sensors telling us we're at. Oh, great. Well, they canceled us. Now they're saying they need the county task force. That's what we had yesterday. The county task force got mobilized, and first responders. It's a glorious life. Let's see. Yeah, so Jason is with Daikin. He's saying that with 32, they've not had any issues with 32 on their side, and I don't know of any machines that have. Yeah, I can't think of any machines that have the 32 or 513 that have like been reporting back any major problems. Which, Jason, y'all are running the, was it 1233 ZD in your low pressure, the YMT, I think? Or was it the 514? I forget. What are y'all running in your YMT series? I don't remember offhand. Can you explain how an economizer will alter your approach? Sure. It's a fun question. Yeah, 1233. Okay, that's what I thought. That's what it was in my head. All right. So, can you explain how an economizer will alter your approach? Yes. Let's talk about the different economizers we have, and we'll just do a real high level overview of the economizers and how that affects the system and why that's going to make your approach have a difference. Let's come over here. So we have two basic styles of refrigerant, specifically refrigerant economizers, not water side economizers. There's a difference. So we have with that we have flash tank, and then we have braze plate. Uh, yeah, braze plate, econo. Sorry, my system keeps going off. Okay, flash tank and braze plate economizers. They do the same basic function, but very different approaches to accomplishing the same effect. Okay, what is our goal for these economizers? It is to increase the efficiency of the evaporator while reducing the total work on the compressor. Let's explain how that works. Now, let's see. Most of Daikin's economizers are. Let's see. Let me think. I guess y'all use both. I say that. Yeah, yeah. I think y'all use y'all. I guess y'all do use both. Depends on the chiller. Okay. Let's start with just a flash tank. So a flash tank, we have a literal tank. So this is our economizer in our refrigerant circuit. We have a line coming out the top. This is our vapor. So it's a medium pressure point. I'll explain this more in a second. Then we have a line coming in from the bottom over here with a metering device. So this is our first stage metering device. And then we have our line leaving the flash tank, which is our with an additional metering device over here. So this would be our second stage metering device. Coming in over here, we have high pressure refrigerant, high pressure liquid refrigerant coming from the condensers. Leaving that, we have a medium pressure. Leaving this tank, we have a medium pressure. And then we're going through the second stage metering device, we have our final low pressure refrigerant. So we go high pressure to medium pressure to low pressure. That's the overall cycle here. What happens is anytime we flash refrigerant, we're having some flash gas. Flash gas reduces the efficiency, or what we call the effectiveness. All right, so we get back into, you're familiar with the term effectiveness of an evaporator. That evaporator is effective. That effective term is coming from the its ability to absorb heat and transfer heat from one point of the system to another. That is a refrigerant's effectiveness. This is also when we get into what is called a pressure enthalpy curve. Okay, you are likely familiar with it. You know, the little curves have this big like U shape, and we draw these little fancy diagrams inside of, and we call this refrigerant circuit. Yeah, this is your pressure enthalpy curve. This will be your pressure. This is your enthalpy. Enthalpy being the amount of heat stored, okay, or the amount of heat. The amount of heat in the refrigerant. So this is our high level enthalpy. So what's happening is as we flash off to a medium pressure, we go from a subcooled liquid refrigerant to a saturated liquid vapor state, or in saturated. We're in between phase. Okay, we're not fully liquid, we're not fully vapor, we're in the middle. Typically, we say there's an 80-20 split. Okay, so that 80% liquid collects here at the bottom of this tank. Okay, so this is a flash tank. So down here we have our liquid. And then all of our vapor collects up here. What this has now done is it's given us a place to separate the liquid and the vapor. Because this vapor, if it is allowed to make it all the way to the evaporator, reduces efficiency in the evaporator. Because this vapor is going to absorb very little heat from the heat exchange or from the tubes. Okay, so let's just use this in a, or we don't even have to go tubes, in the heat exchanger, whatever style of evaporator they're using. I don't care. This vapor does not, it limits how much liquid contact we have with our heat exchanger to transfer heat from the water to the refrigerant. So because of that vapor, we lose efficiency. That's one phase of this process. So what this tank is doing, it is allowing us to supply a full, or get rid of all that vapor flash, the flash vapor, and give a full column of liquid to our primary metering device, or the second stage metering. And from here, we go through the final process to go from medium pressure to a low pressure refrigerant. Now, there is still a flash here, but it's far less. It's much less of a flash because most of the time this stage gets us most of the way there. Like we go from, let's say, 100 degrees of saturation down to like somewhere in the 60s degrees here in the medium pressure zone. And then from there, once we go through the second stage, we'd get down into the 40s. So from 60s to 40s, which ultimately we just have less flash gas in the system compared to going, say 100 degrees of saturation down to 42 degrees of saturation, right? Or 40 degrees, whatever you want to use. Like, instead of having to make that full jump in just one swoop and all that flash gas make it to the evaporator. So that's where this metering device comes into play, and then gets us the rest of the way in the evaporator to improve efficiency in the evaporator as a total. So we have a higher concentration of liquid to refrigerant gas, or liquid to vapor refrigerant. There's a higher concentration of liquid making it to the evaporator than there was if we didn't do this. Now, what this also does is this vapor that we pull off goes back into an economizer port on the compressor. That economizer port means that we don't have to take this refrigerant. It's not sent into the suction, like the same suction that the low pressure is. Most of the time, this refrigerant is sent to a midpoint, and it's only having to be compressed from medium pressure to a high pressure instead of from low pressure to high pressure. Well, that just means that the compressor had to do less work. Less work was performed. It had to work less hard, just all the various ways I'm trying to say this, so that we could get the refrigerant back up to a high pressure state. And if we didn't have this tank in between, all of that refrigerant, 100% of it has to be pumped back through the compressor from low pressure to high pressure. It takes a lot of electricity to do that. Compared to, it takes a lot less electricity. I say a lot less. It takes less total electricity to take this medium pressure to high pressure and have a combination there. Okay. Now, back to the core question. Explain how the economizer will affect your approach. So, in a scenario where we have this machine here, This economizer is only engaged part of the time. It's not engaged all the time, only part of the time. So because of that, uh, you'll see this if either one, the economizer fails. All right. So for example, this line up here has a control. There'll be a valve of some kind controlling when this economizer is active. When it is inactive, it basically the machine functions like it normally would, but that's only at lower loads. So the chillers on the market only use this economizer once we get above a minimum load. Once we're above that minimum load, then we open our economizer port, leaving, pulling the vapor off the tank, and start the economizing process. So two things, either when we're not using the economizer or when the economizer valve fails, we're not getting all of that, or we are getting all that vapor back to the evaporator. And what that causes is higher approach values. That's the core premise to the question. If the economizer is not working or working correctly, it increases approach in the evaporator because we have a higher concentration of flash vapor making it to the evaporator. It is as simple as that. There's just higher concentrations of flash vapor that makes it to the evaporator. That higher concentration reduces the efficiency of the evaporator, which we get back into our PE chart here. And this is a whole explanation breakdown in and of itself. By the way, I cover all of this in my certification course, right? So all of these are things that we're going through. I show you, I break it all down just like this in that course. I have a whole module dedicated to just economizers alone. If you want to get in there, check that out. That's at chilleracademy.com. Okay, so that's my online chiller certification course. The whole goal for that course is to get you, an HVAC technician, from where you are, maybe you're in the RTU realm right now, and to help you make the transition over into chillers, be fully trained, educated, understand what we're saying, understand how these machine works. Like that is a full all the way around course built to get you there. I personally teach that course all the way through. Like it is me. I do it all this, and I'm not AI. Like I'm real flesh and blood here. Not really into the whole AI thing all that much. So anyway, yeah, if you like really want to break down, go check that out. That's the high level of what a flash tank is doing. Now, a braze plate is slightly different, but a lot of similarities. The end result is the same. Ish. The same ish. Okay, we're going to leave our PE chart here. This is also sometimes referred to as a pH. Okay, so just bear that in mind. Some of us say PE, some of us say pH. You could hear either term being used, and we're saying the same thing. The E or H is referencing enthalpy, either way you slice it. Okay, so with a braze plate, I'm going to draw like a frontal view of it. What we'll have is I guess I can get some colors involved here. Coming in from the condenser, we come in and hit our liquid port. So this is from, this is our liquid line. I'm just going to LL from the condenser. And then down here, we're going to leave colder, so more subcooled. So let's say we went from 10 degrees Fahrenheit subcooled to down here we're at 20 degrees. Okay? And then we process through a metering device. So this one would be considered our evap MD. Okay? And then in here we are processing through the heat exchanger, braze plate heat exchanger. Okay, so brazed plate. Now, part of what makes this different is we're going to have a line come off our liquid line coming from the condenser.
come down and feed into this bottom port down here. And guess what? There is a metering device. So this would be our Econo MD. Okay, this is feeding for the economizer. Now in modern chillers, this is a EXV. In older machines, you're going to see this with a TXV and a solenoid valve. Okay, so all your modern chillers, it'll just have a single EXV, and that EXV is your control valve. So it'll fully close to isolate flow if needed. If it has a TXV, then you'll see the liquid line or the solenoid valve, and that will open and close when it's time to run the economizer. Same thing I talked about with the flash tank, where with the flash tank, we would activate the vapor leaving line going back to the compressor once we got above a certain load, once the compressor or the circuit load got high enough. Same exact concept here. This EXV will stay fully closed until we get past a certain point. Then it gets triggered to come on, and it'll start to flow refrigerant and function. Okay, so then we leave. So this is coming through this way, doing its braze plate thing, and we leave and go back to the compressor. The compressor economizer port specifically. Okay. In short, what we're doing is we're taking a little bit of liquid refrigerant from the condenser. We're sending it through, not as a low pressure. So that is one thing. Like most of the time, these are going to be at a medium pressure state. We're still at medium pressure. So, because here's the thing. This is not an evaporator. We're not trying to achieve, 45-degree water leaving this heat exchanger on our liquid line. That's not what we want. We're wanting to go from, let's say this is 100 degrees liquid line coming in. We're trying to go to 90 degrees. We may only need a saturation of, let's say, 80 degrees Fahrenheit to accomplish that. Does that make sense? So don't think of this as this is like another low pressure circuit. No, this is a medium pressure circuit, and our saturation is relevant to whatever we're trying to achieve on the leaving side of it. So if we're wanting, like I said, 90 degrees leaving liquid temperature, or I'm just picking numbers here, so adjust your numbers accordingly. You can measure this in the field. You can go take a reading across here. Like you can just do your own discovery here. Anyway, so we have this economizer circuit is a medium pressure circuit that we send back to the economizer port, just like a flash tank did. And essentially, we're using the PE chart, but in just a slightly different way. Where yes, we have 100% of our flash vapor coming from the liquid line, or actually that's not even true. Because we're using this extra circuit, some of that flash vapor that with the flash tank economizer, we're separating it. With a braze plate economizer, we're just using it for refrigeration effect. Okay, so we're actually refrigerating that liquid line down to get it colder. By getting a medium pressure, lower saturation. So because the saturation is lower on the economizer circuit, we still transfer heat, even though we may have a saturation of 70, 75 degrees of economizer saturation. It's still colder than the liquid line, and that's all that matters. It's colder than the liquid line. So this medium pressure flash gas doesn't require as much work to get pushed through the compressor. Simple as that. So the compressor work is reduced in that way. In addition, we make the economizer or the evaporator more efficient because by lowering our subcooling, we're increasing the refrigerant's ability to be efficient in the evaporator and how it functions on this PE chart. Again, I have an entire lesson dedicated to this in my certification course. You can go jump in there, and I fully show you and explain all this in much better detail than I am at the moment. Right now, I'm just doing a really fast overview of the basics of how this works. So, again, just like with the flash tank, the when this is not functioning, our approach values do increase. Coming back to the core original question, can you explain how an economizer will alter your approach? So when this is not online, or let's say this EXV fails and it won't work, the approach specifically gets increased because we're not able to control our PE relationship, pressure enthalpy relationship, the same way. And we're letting a lot of inefficient flash gas make it to the evaporator that isn't meant to be there. And that is increasing your approach value on that evaporator. And as soon as this economizer kicks in, or it gets back into functioning, once the circuit gets enough load on it, you'll see that approach come back down. Yeah, that's my very basic high level overview of how the economizers we use will affect approach in your evap. Greetings from Germany. How you doing? Currently repairing an RTAC 165, replacing the GP2 sealant and doing an oil change. Our problem is I didn't get any oil out. Okay, well the oil is probably in the evaporator. Yeah. So if you didn't get any oil out of the compressor where the compressor circuit is, or if you didn't get oil out of the oil separator. All right, so we said RTAC. I think, let me verify something real quick. Okay, I see RTAD. Yeah, so either way, you've still got an oil separator in that machine. So if you're not getting oil out of the separator or out of the compressor, it's in the evaporator. Assuming the machine was working at some point prior to you getting there. If it hadn't been working for quite some time, who knows what happened, right? Maybe the oil's gone. But if you're not getting oil out at all, and if it's in the evaporator, then you have to go through the oil recovery process, which most of the time it means getting the machine online. I don't know if that's even an issue. You said you're replacing the sealant and doing an oil change. So it sounds like you're just there doing some maintenance work and such anyway. So if that's true, then if you get the machine online for a little bit, let that compressor run with a load ideally. Like that would be best. Let it run with a load for 30, 45 minutes to an hour, and you should see that oil return. And if it legit has no oil in it, it's not going to run for very long before it's going to trip out on oil flow issues. So that's what I would suggest there. Verify sensors, transducers. Yeah. Quite a big leak, but I'm refusing to think 25 pounds of oil just vanished without anyone. Yeah, I doubt it. I agree with you. It's not very likely that oil just, even with a decent leak, like it's mostly going to be refrigerant leaking with a little bit of oil. And it's like, it doesn't take much oil to make it look like a lot of oil. Which it sounds like you know that, right? So evaporator, like that's where I go with it. That oil it got migrated or stuck in the evaporator for some reason. Separate oil from refrigerant. Check the bottom of the evaporator. Yeah, there you go. Opened oil filter, oil separator, also washed. The oil cooler with nitrogen. No oil at the lowest point of the line, liquid line. Also, no gas pump installed. Yeah, so we keep getting back to the evaporator there. And that's usually when the oil migrates, that's where it typically migrates to, is the evaporator. We have two modes on our EXV control, superheat and pressure. If you have a low pressure evap, pressure issues, EXV will open to maintain pressure above freezing. Yep. Do you evacuate refrigerant from bottom? Let's see, let's chase this down. Didn't evacuate refrigerant since it was all gone, so no oil in my bottles. Flushed it at around 3 minutes with about 10 bar of nitrogen. But yeah, even with, okay, so it's a fair point. Now you say it's not flooded, but a direct expansion evap, so you still have a shell and tube, refrigerants inside the tubes. It'll still migrate oil and stack in that evaporator. It is different. It's different than a flooded. You're absolutely right. We don't have any ductor circuit. We get that oil back through through the velocity through the circuit, which again, it means getting the circuit back online if possible. But those will absolutely still stack oil in those tubes, just the same, or in the same basic way that a flooded would. It's just the process of getting it back out of there is a little different. Yeah, RTACS flooded evap, AD, yep, that's right. So in Germany, you have to install kind of oil pan under the machine to catch any oil. Oil gets reduced. All the rain, snow, yeah, 25 pounds should still be visible. Absolutely. I still stand on there's a high likelihood, especially if you've got some cold, which I mean, obviously you would. You're in Germany and it's February. So you're in the time of year where it's very, very common to have migration like that. So even though it's a DX, again, unless the machine was recently online, right? So if you walked up, it was already running. I could just, if it was running at a really low load and it was heavily unloaded, when you turned it off, that can still happen. You can still have that oil migrate and get stacked in that evaporator. So all of that can still be true. Just be very, very mindful of that. Just because it's a DX doesn't remove the possibility. It just changes what it looks like a little bit. So yeah, I would just I'm still thinking evaporator without just more information with what you got. Do you evacuate refrigerant from the bottom of the evaporator or did? Oh, I see. You're asking. There's a pipe at the bottom of the evaporator. Oil returns. Yeah. Okay, didn't run for several weeks. Okay, that was my initial instinct. It's been offline. So, like I said, I'm not saying I'm absolutely right. I'm just saying that there's a high likelihood that oil is in those tubes, and usually what I see is it stacks in there at the bottom of the tubes. Now, in order to get it, like the only way to get that out, quite literally, the only way to get that out, in my experience, is to get the machine running. But you're already there trying to do an oil change. That oil is going to contaminate the old or the new oil. If so, like you're really in kind of a lose-lose scenario. It really sucks. But if I'm correct, part of what you would see is when you do get the machine online, you're going to go like all your new oil to show good levels. You're going to see like all of a sudden it looks like you overcharged it or you added a lot more oil than you know that you did. When you see that, that's when you know that oil returned. And so, and I guess okay. Let me draw this. Let's just draw it. So we've got our evap. We've got our tube bundle. Okay. So metering device, suction line coming out back to the compressor. Okay. Usually what happens, so we've got to get that oil all the way back up here, but what can still happen is that oil will still get pulled into this evaporator in low ambient conditions, similarly to how a flooded would. It's not exactly the same thing, but it's very, very similar. And so it'll still migrate and stack in here. It's a pain in the butt. So it doesn't always stack right in this bottom tube though. Okay. So depending on how perfectly level and how the tube bundle sits in there, it may get caught in these zones here. And it may not actually be something where even if you opened it up at the metering valve, you would get all that out. And now if you purged through the evaporator, like if you wanted to put the effort and the work in to try to do that, like if you could purge from the suction back out through the metering device, there's a high likelihood you could push a lot of that oil back out of there. It's very, very true. Um, but it'll still migrate and stack in here. And then to get it back out, once we get the machine online, get a little load on it, get our head pressure up. So if you're having a low ambient condition, you're going to want to force a higher head pressure. That higher head pressure is going to then allow that oil to then fully migrate up. And with these, it doesn't take as long as so think in RTAC, yeah, that oil recovery line could take 30 minutes to an hour. With these, you get that head pressure up, you can get that oil back in like 10 minutes. It doesn't take long once you get the circuit loaded up and you get the numbers just right. That oil will come screaming back to the compressor in a positive way. So it doesn't take long. It's just, I don't know how effective trying to purge. I've never tried to do it that way. When I've had these conditions, I've always just brought the circuit online, or like when I've had your scenario, so I've had compressors fail. I needed to go in, do an oil change, put the new compressor in. Oil had migrated. It was bad contaminated oil. What that turned into is just a couple of oil changes, right? So that is the alternative to doing the like a purge of the oil, is just to do it through oil changes, right? That's been my preferred method. That's how I was taught. I did the purge stuff in the beginning, and I switched to just changing the oil with runtime. Again, context matters. In your context, that might not make the most sense. I'm just saying in general. And so you may have to do one or two more oil changes to fully get all that oil out of there. And that's what I knew to expect. I know that, okay, I've got contaminated oil that I can't get out of the system. I have to get it running. We're going to put the fresh oil in. I'm going to put some neutralizer in with it. And then I'm going to come back in a week and I'm going to change it again. I'm going to do it again in probably a month after that. And we'll see from there how the condition of the oil is doing. But there again, you're probably in a scenario where running it's not an option. Sounds like you're likely in a seasonal shutdown. I don't know, but it sounds like. So you may not be able to do any of that until closer to the summer. That's why I check the liquid line close in front of the open DXV to see if it will flow. Okay, so you already tried doing some form of the purge. Yeah, that's the issue, because there's just so many tube bundles. Like, because of the way those bundles line out, trying to do a purge, like that oil just it gets spread so much throughout those tubes. Yeah, I'm not surprised that trying to purge it didn't work. That's one reason why I've just never really tried, because the oil is not concentrated enough in here to make purge really all that effective. Oh, it's shut off because of leaks. Okay. Well, if yeah, if you can get it online, like, just something to be aware of. Honestly, from sounds like you've done as much as you can do. Like, you've done a good job. What I would like, if I was in your position with what I have, and I don't have all the information, but from what I understand, I would just finish what you're doing and get it back online as when you can. If that's not today, like it's got leaks, I get it, but when you can, try to get it back online and monitor that oil. That would be my next step in your position. That's what I've done in the past. PSIG of nitrogen did you put through? You got oil recovery lines below the evaporators. Service valves at the bottom. Da, 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 da. All right. Yeah, I mean, if you, by the way, I appreciate you jumping in. Uh, Hopefully, we're all coming from a place of like just we're interested, we're techs, we're trying to help, we're trying to troubleshoot. We're not there, not coming from a place of trying to tell you what to do or what is, what isn't, that you're wrong, right. None of that's true. I just want to say that out loud, make sure we're all on the same page. Like the goal here for this kind of stuff isn't to you're right, I'm wrong, or take any kind of approach like that. It is strictly, oh, that's really intriguing. We get excited, dog on a bone, and that excitement can sometimes come off as aggressive, right? I know that I do, and it's not meant that way in any means. So just putting that out there. All right, let's check in on the fire real quick. Let's see what the most recent update was. We still got the task force mobilized. Yeah, they're bringing the county task force in. We shall see. I'm sure I'll hear about that one later. Yeah, appreciate that. Love the work we do on socials. I've been doing HVAC for 10 years. Began my chiller journey about 4 years ago. Awesome. Well, hopefully it's going well. And you're getting to have fun. Like, that's the whole point of a lot of this. Let's have fun. You know? All right, let me grab. So I've got one question that I've been needing to get to that I've really been interested in talking about because it kind of annoys me. Okay. The question doesn't annoy me. It's the narrative that's been out there is what annoys me, just to clarify. I'm not annoyed by the question. I think it's the right question. I just you'll get it in a second. Okay. Can you explain why data centers have to plan to use millions of gallons of water per year? Are they just losing that amount of water due to evaporation? Okay. So there have been numerous reports that I've seen in articles and stuff and studies that are trying to claim that data centers are going to use this ungodly fathomable amounts of water to function. Mind you, less water than a lot of our other infrastructure does. Okay, if you really actually look into the data, we're talking power plants, stuff like that. Less water, but still lots of water. Here's a huge part of the issue to this narrative. There are still plenty of large data centers that are water cooled. But there are a whole bunch, especially these most of the ones getting built that I know of that I've been consulting with, like a lot of them that are getting built right now are not these mega centers. They're these smaller centers. Now, they still need a lot of cooling. But guess what? They're using air cooleds. They're all using air cooleds. Not all, okay? I'm saying these smaller ones. These smaller ones are using air cooled machines. Now, there may be 50 freaking machines on one data center, but they're air cooled. And what they're coming back to with all of the studies I've seen, maybe there's some that have done this in a better way, but all of them that I've seen, somebody did just enough Googling to understand that data center use is uh, the GPUs they're using for these data centers and these servers, they use X number of watts. Watts equals heat with electronics. It takes X that heat that watts equals the BTUs. BTUs needs X amount of water to cool said BTUs, and so for every watt being generated, we have to use X amount of water to cool said watt of power used by the GPU in order to feed the internet, the AIs, and everything of today. And so, hence, all of these watts means we have an equivalent all of that water being used up everywhere it's at. And that's just not true. That's not the way our system works at all. I'm trying not to get over the top. I'm really not. But we do have some system. There are plenty of data centers out there that have water cooled machines. These are very large centers most of the time, and yes, they lose water due to evaporation, just like every facility and industrial complex that exists out there. Absolutely, absolutely. But the vast majority, especially for what is being built right now, they are using some level of air cooled machines. Now, they may have large loops, but guess what? The loop, as we all know, gets filled once. Maybe you have to service it, you lose some water here and there, but you fill it one big time in the beginning. One. And we recycle that. So it's not that so much water is being used per to cool all this new water, because that's kind of the approach that these articles take, is like, oh, it's taking all this extra water. No, it's that same gallon of water might process through for years. That same gallon, same cubic foot of water might process through a loop for years on end and process huge amounts of heat and not actually be evaporated or used up. It's just recycled, and we chemically treat it to help it be stable throughout the system and not wear stuff out. That's what we're talking about. But again, whether these I honestly I think that a lot of these articles that we see are they're intentionally misleading because somebody has a narrative that they want you to believe. There are people in the world that benefit from AI not thriving, that benefit from these companies not doing well. There are a lot of special interests that are benefited from them being slowed down. So they want public opinion to slow them down. Now, I'm not taking a side on the fence here, okay? I'm not. I don't have a stake in this horse or a race or whatever you want to say where I'm advocating for the data centers, and I'm not advocating against them. I'm not. I really don't have a position. To me, it's just my main issue I have with data centers right now is we don't have the workforce. That's my issue I bring up. We do not have enough of us that are trained, have the experience. Like the data centers we don't have enough technicians to support them, in addition to all the other infrastructure we got to run. So if we're going to do all of this work, how about we take some serious initiatives and build our workforce, get everybody better trained, get more people in? How about we do that? How about we really work on better pay, better benefits? How about we do all these things so that we can then support this infrastructure being put in? Otherwise, if we can't turn it on, what's it matter? That's my position. That's the gripe I make with it. And that's a real issue we should be talking about, not this millions of gallons. Again, I don't even say that it's just strictly because of ignorance. I think it has more to do with these are what major corporations do to compete with each other. They know that they have to shape public opinion to their way. These AI companies are trying to shape our opinion to make us like them. And these other companies are trying to shape our opinion to make us dislike them, and they're having to fight each other. And this is ways that they do that. And they're trying to convince you that they're right and the other is wrong. and their zero sum games that they play. So, my point being, all of the nonsense about extreme water usage is not true. It's just not. And there are some minor truths, and that's part of the thing. There are some minor truths with some of these centers that I consult with. Like, there is an agreement with the local utilities where, hey, we have to fill up this loop. We're going to be using some serious water. Help us do that. Sometimes they ship water in. There's various ways that we can get the water into the system and be very mindful of how it affects the local utility. Lots of times that's coordinated, and it's required to be. Otherwise, they get in trouble, right? So, yeah. There are way more air-cooled data centers than there are water-cooled. Just saying. That's yeah. Finally got to get that one off my chest. I've been waiting to answer that question for quite some time, and I get so, I see all the like you said, propaganda. Excellent phrasing, and it's frustrating because it's just not true. Use air cooled chillers so the water cool is a closed loop. Yeah, exactly. No water wasted. Right. I've recently moved into the position of Daikin, and I'm going to start working on larger chillers a lot more. I've been binge watching your channel to learn as much as I can. Yeah, excellent. Congratulations. And I mean, hey, check out Chiller Academy, man. I try to do as much as I can over there. Between posting articles, I do have a email tech letter I send out every week. I don't have an open like public enrollment for that yet. I'm still working on that, but if you reach out to me, I can always add you to that list. So that's kind of how I'm currently doing it. Is like, once you enroll into the academy, into one of the courses, or if you ask, I can add you to it, but I haven't set it up for like public add yourself to the list yet. But I mean, those are things like I highly encourage you go engage with that, and that is what the whole concept, the whole purpose is to get this information, the education, everything out there, so that you can do something with it. You can take care of yourself. We're not so dependent on the manufacturers and our companies having to support us all the time. That's part of what's gotten us into this position, is either through gatekeeping or just not supporting the technician, either or. We've not properly trained sufficiently, and we're not properly getting the right information where it needs to be. So my mission is to fill that so that all of you have the ability to self-support yourself, and you can bypass all the traditional methods that would have kept you out otherwise. It would have given you nothing to go off of, and just figure it out or drown. Like, that's what we had, and I'm just not okay. I just don't think that's the way forward. That's why we're in the position we're in right now, in my opinion. So anyway, I need to wrap this up. I really appreciate everybody's time. Really fun chat today. Enjoyed everybody's engagement. And yeah, have a good week. I will see you MTT. Make the time for your family, for your spouse, for your kids. They need you. Make the time. It's not going to be there. Take it seriously. See you guys later.